Okay, now, so all these parameter in our objective to find the design wind pressure, we now is already calculate V dash, whereby we have V dash. Now we already know what is our zero point 0.5 density of air, which is 0.613. So the next thing that we need to find is the Cfig, which is what we call as the aerodynamic shape factors. Okay, so Cfig is the aerodynamic shape factors where we need to calculate based on section 5. So now let's calculate Cfig. Okay, let's now calculate our Cfigs. So just to recall from our lecture, Cfig is the aerodynamic shape factors. So please refer to our notes, whereby the aerodynamic shape factors given in clause 5.2, okay, which is this clause, okay, clause 5.2, evaluations of aerodynamic shape factor. So in that, you have two categories, which are enclosed buildings or freestanding hoardings, walls, canopies, and roofs. So, in our examples, okay, in our examples, we are dealing with the totally enclosed building, which is a building itself. So, because of that, we have to refer how to calculate the Cfig for category 1. Let's say we are designing a structure, okay, for instance like a signboard, which is categorized under freestanding hoardings, or when we have what we call that, like kenduri and so on. So we can have the canopies, roof, because we have to make sure that it's not um, flying during the event and so on. Okay, so for our case is enclosed building. So then we have Cfix is equivalent to CPE, KA, KC, KL, and KP. And for external pressure. And this one is for internal pressure. And this one is the for frictional drag forces. So basically, we have to find what is the CPE, KA, KC, KL, and KP. Okay, to calculate the C factor, which is the aerodynamic shape factor, it is based on these equations. So now let's find what is our CPE. Just to recall in our notes, okay, CPE is the external pressure coefficients for enclosed building. Okay, so in the dynamic wind pressure, it says that the kinetic energy will convert to potential energy, and that the conversion is not 100%. As we know, when a wind load is acting on the structure, okay, the wind pressure will not convert 100% as a kinetic energy. Okay, so this is because they are contribute from the external pressure coefficient CPE, which is what we call as a degree of the conversions. Thus, for any external surface, we can write with this equation: wind pressure CPE times kinetic energy. So CPE is equivalent to these equations. For an enclosed building, it is possible to divide the external surfaces into windward and leeward wall, side wall, upwind roof, downwind roof, or crosswind roof, as shown in figure 5.2. Okay, so if you can see here, this is what we call, we have figure 5.2. So here figure 5.2, where you can see W, okay, which is indicate W. W means windward, all right. And if you can see L here, with this directions, this is the leeward, and S is the side wall, and U is the upwind slope. So here you can see in the guidelines, there are variety types of enclosed building, okay, which this enclosed building is subjected to the windward and leeward. So windward, okay, if you can see here, windward is, this is the arrow showing the directions of wind. So the face which is the face which is facing the wind directions is what we call as a windward, and the back face which is in these directions, okay, in these directions, is what we call as a leeward. Here is the side wall, which is the face where it is parallel to the wind directions. And if you can see here, U, okay, U is the upwind force surface, whereby when you have the wind load, it is come and it will go upwind surface. And here is when you have the wind load, some will go upward, okay, some will go upward, something like this. Some will go moving upward, the directions of wind. It's come from here and it goes upward. And some can go downward, okay, some can go downward. So here is the definitions of the windward and leeward sidewall, upwind slope, and so on. Okay, so here is indicate B and D, and this is what we call as a height. So now let's look at table, okay, table 5.2. okay, so let's look at table 5.2, which is this table. Okay, so this table is the table where you wanted to find what is the windward wall, the external pressure of CPE. So here is the coefficient, and also the leeward wall, which is the external pressure, which is this is the coefficients. So if you look for the windward wall, okay, the external pressure is depends on the height, which is either it is less than 25 meter or it is more than 25 meters. If it is less than 25 meters, and you have to look whether it is for buildings on ground or for elevated buildings. Alright, so in our structure, our building is more than 25 meter because it is 40 meter height. So because it is more than 25 meter, so therefore our CPE for windward wall is a 0.8, which is speed varies with height. So now from table 5.2 for windward wall, okay, so windward wall, we can get that our CPE, okay, is equivalent to 0.8. okay, and because the height is larger than 25 meter. So now let's look at the leeward wall. Okay, so now let's look at the leeward wall. So this is table 5.2a. So now let's look at table 5.2b. Okay, 5.2b, whereby we have the leeward wall. Okay, so table 5.2b leeward wall, you can see here. Okay, you can see here. So here it depends how you categorize, how you find the factor, the external coefficient pressure factors. It is based on the angles of your roof and D over B. So if you look, okay, if you look this, okay, in these structures, okay, so here is D, here is B, all right, and here is D, here is B, and this is what we call as the angle. If your structure have a slope, okay, I mean the roof have a slope, then you need to know what is the slope of your roof. Like you can see the slope here. This is the slope as well. Okay, so in our structure, okay, we have a tall building structure which is H is more than 25, and this is the windward and this is the leeward. Okay, so in our structure we have no slope because the building roof are flat. Okay, so if you look at this structure, okay, if you look at this structure, all right, so we can see that our slope is categorized less than 10, our D over B is you need to go to this, okay, this back. So which is our D, which is our B, okay? So sometimes students, they are confusing how to define whether this is D or this is B. So the tip is that you have to look at the figures, okay? You have to look at the figures. So where is your wind directions? So in this case, this is your wind directions. So meaning that this is your wind directions. Wind directions. So because of this is your wind directions, okay, you look back here. So since that is your wind directions, so that is the windward. So when that is a windward, all right, so that is a windward. So the one that facing the windward is B, okay? If you see the one which is facing the windward, so this is the wind direction, this is the face which facing it, that is B. And the one is just parallel to the windward is what we call D. Similar here, this is the face facing the windward, B. This is the face which is parallel to the windward, which is D. So here are the faces which is facing the windward. Faces that facing the windward, okay, faces that facing the windward is we define as B. So this is your B. Faces which is parallel to the windward is what we call as D. So this is D. Okay, so now let's calculate the leeward wall. So for the leeward wall, okay, we know that for our structure, the angle which is less than 10 degrees, okay, because the slope of roof, okay, alpha is equals to 0, because you can see our structure, okay, our structure, there is no slope, as has been explained earlier in previous figure. All right, so then our D is given as 12 meter, B is given as 8 meter. So then we have the ratio D over B is equivalent to 12 over 8, and we then finally get 1.5. all right, so in here we have D over B, so we have to look back at our table 5.2. okay, now you can see table 5.2b. okay, so for table 5.2b, okay, alpha is less than 10, which is our conditions, and D over B, okay, D over B we have 1.5, okay, 1.5, which is it is in between 1 and 2. So we have to do the interpolation between 0.5 and negative 0.5 and negative 0.3 together with this and this. So by you doing the interpolations, okay, by interpolations I have previously calculated, so you will get the CPE value is equivalent to negative 0.4. okay, so you will get negative 0.4 in between. all right, so then you have the CPE value. So now we know that we already have our CPE value. So what is our KA value? all right, so KA, okay, we wanted to know what is our KA. all right, so KA, if you recall into our lecture, if you refer to our notes, okay, KA is area reduction factor, whereby it is given in clause 5.4.2, and local pressure factor KI is given in clause 5.4.4. So what does it mean by area reduction factors? So here are the explanations. It's saying that the dynamic pressure is not uniformly distributed. Yes, of course, because if you look at our buildings, okay, the dynamic pressure can be growing like this, or it can be like this, or you at some point you may have a building where it is like this, and it is depends, and it is fluctuated. okay, it's not uniformly distributed. So different external parts of the building are subjected to different dynamic pressure, at a particular instance of time. Bigger exposed surface area to wind will have higher probability that dynamic pressure will exhibit non-uniform distributions. So when you have a surface which is more exposure to the dynamic pressure, then therefore it will exhibit non-uniform distributions. On the other hand, small exposed areas such as window panels, okay, will have high probability of having uniformly distributed loading. So what I'm trying to say here, okay, if you look at this figure, okay, so large exposed surface area, example wall, okay, example wall has more non-uniform distributions. So you have a wall, so it can be non-uniform, this is pressure, so non-uniform distributions of wind pressure, smaller average pressure. But when you have a small, for instance like only the window exposed surface area, has more uniform distributions of wind pressure, which is bigger average pressure. So if you look at these distributions, okay, the pressure is increased when it is at the windows area, and it's try to move down back when it is no opening, okay, no window, so it just has the wall, and then no opening, so it's going down, and then it will try back pressure when you have the opening. So basically, small exposed surface area, which is this area, which is very small, exposed to the wind pressure, okay, has more uniform distribution. It tries to get a uniform distributions, rather than when you have this, it will have like a fluctuation. Okay, so in addition, okay, in addition, for any given surface, different parts of the building experience the maximum pressure at different times. Again, the effect of these non-simultaneous actions or non-uniformity over time of the wind, okay, is bigger when the surface area exposed to wind is bigger. Okay, the keyword is that when the surface area exposed to the wind is bigger, then the wind is bigger. So as you can see here, again, time t1, so when the average pressures come in, okay, time t1, the pressures come in, and at time t2, okay, for instance this is 5, and then this is 10 minutes later, you can see that the large areas such as entire building can be designed for P average. So this one you can design for P average, but the small area, it will increase, the pressure at small area will increase. Okay, so small areas such as windows must be designed for P max, okay, because it will increase, and in some cases magnify by local pressure, what we call as the K local. Alright, so that is what the KA means. Okay. Therefore, if you look here in our notes, it is apparent that surface area is important factor in determining the average wind pressure on a surface at any instance of time. So surface area is very important. Bigger surface areas can expect to have a lower average wind pressure. So bigger surface area, lower average wind pressure. The area reduction factor, which is Ka, the one that we're going to determine, Ka, accounts for this area effect. The bigger the surface area, the smaller the area reduction factor. So this is the keyword. The bigger the surface area, the smaller the area reduction factor. Alright. So on the other hand, wind pressure on small areas such as claddings, roofing sheets, or certain localized areas of surface will have high probability of experiencing the maximum possible wind pressure. The average wind pressure should not be applied to this surface. in fact, the wind pressure in this localized area, called local pressure, can sometimes be much higher than the average pressure and is accounted for using local pressure KL. Alright? Okay, so now let's look at KA value. So for KA value, okay, we then look at the clause 5.4.2 to determine KA. Okay, so refer to clause 5.4.2. Okay, to determine KA, refer to clause 5.4.2. And from the clause 5.4.2, where is the clause 5.4.2? Because this is the clause. Okay, if you look here, MS 1553, clause 5.4.2. So area reduction factor. Okay, so tributary area. Okay, what does it mean by tributary area? So you have to read the clause. Okay, for roof and side walls, the reduction factor KA shall be as given in table 5.4. Okay, shall be given in table 5.4. For all other cases, KA shall be taken as 1. So tributary area is the area contributing to the force being considered. So in our case, okay, our KA is equivalent to 1 because we are designing for other cases. Okay, so now we know that our KA is equivalent to 1.0. So next, so we have done our KA, so then we find what is our KC. So to determine KC, okay, so KC you have to refer to clause 5.4.3. So for clause 5.4.3, this is the clause, okay, for you to determine KC, okay, which is the combination factor. Alright, so in this case, where wind pressure acting on two or more surfaces on an enclosed building, that is windward wall, upwind, roof side wall, internal pressure, and etc. Okay, so meaning that if your wind pressure have a different angles and so on. For instance, if you look at the figures earlier, whereby we have the figures, okay, like this, you can see these figures. We have the windward side wall, and then the wind can acting the leeward as well, upward. So that is the tributary area. Okay, so in our case, that is the surface. So in our case, okay, we have a combined windward leeward, and we neglected the effects of roof. Alright, so we neglected the effects of roof. So in this case, okay, we can see in our cases where wind action from any single surface contributes 75% or more to an action effect, it is 1. Pressure from windward and leeward wall is in combination with positive and negative roof pressure. So meaning that if you have a windward and leeward, and then you also contribute from the positive and negative pressure, which means you are considering as well the upside wind and downside wind. And for this, okay, is positive pressure on roof in combination with negative internal pressure. So meaning that you have a slope, and then you have the positive and negative pressure. Negative pressure on roof walls in combination with positive internal pressure, meaning that you consider the windward and also different design phases whereby you get internal pressure as well. So in our case, we are choosing all other cases 1, okay, because in here for these examples, this is very straightforward examples, we neglected the effects of roof and also the internal pressure and so on. So because of we neglected that that effects, so therefore we choose our value as is 1. But if you consider if you have the combinations of windward and leeward also with the negative and positive pressure, so you have to choose your KC value accordingly to your specific situations. So therefore in our case, KC is taken as 1 as well. Okay. Alright, so then we now have our KC is equals to 1. Okay, so then we done for our KC. Okay, so now calculate for KL. Okay, KL is the local pressure coefficients. So as explained earlier, the local pressure coefficients, okay, is only determined for small applicable to cladding, and it is not for a building, okay, as we have explained earlier. So then to determine KL, okay, so you have to refer to clause let me check it, okay, 5.4.4, okay, to refer to clause 5.4.4, where this is the clause 5.4.4, okay. So local pressure factors KL for cladding, okay. The local pressure KL shall be taken as 1 in all cases, okay, except when determining the wind forces applied to cladding. There are fixings, the members which directly supports the cladding, and the intermediate fixings of these members. In the cases, KL shall ideally be taken from. Okay, so here local pressure for claddings. Okay, so this is examples whereby you have a cladding and you need to analyze those structure. So class 5.4.4 in this case give you KL equals to 1.0, okay, because the local pressure only applicable to claddings, not the whole building. Okay, so then you have settled that, which is your KL value, and then you can go for a different clause, which is this is 5, this is 6. Okay, so then you need to find what is your KP to determine KP. Okay, you need to determine KP because you now has already KL. So just to summarize, okay, you need to find your KP. So KP you need to refer to clause 5.4.5. okay, clause 5.4.5. so in this is actually a porous cladding reduction factor, which is the cladding of the building reduction factor. So because our building is totally enclosed, okay, the building totally enclosed, okay, so therefore we take KP equals to 1.0. So you should refer to clause 5.4.5. So to summarize, okay, here, let me use a different color. So then you already have your CPE, where your CPE is negative 0.4, okay, here, which is your CPE, negative 0.4, and then your KA is taken as 1, okay, 1.0. Your KC is equal as 1, and KL also equals to 1, and KP is also equals to 1. So finally, it gives that your CFIC, okay, your CFIC for windward. So then you calculate your CFIC. Okay, calculations, substitute. So now we substitute the value into the equations. Okay, substitute the value into the equations, which give CFIC, which is the aerodynamic shape factors, which is CPE, KA, KC, KL, and KP. Now you get CPE. Okay, sorry. This is CPE for, here is CPE. We have two CPE. CPE negative 0.4 for leeward, and you have another CPE, okay, which is 0.8 for windward. So CPE, you have two values for windward wall and also for leeward wall. Okay, so then substitute the value into the equations. So let's first calculate for the windward wall. Okay, so for a windward wall, you have 0.8 times with 1.0 times with 1.0 times with 1.0 times with 1.0. So finally you give you 0.8. Okay, all right. And then for the leeward wall, okay, okay, for a leeward wall, so this is CFIC for windward, and here is CFIC for leeward. So CFIC for leeward, you have negative 0.4 times with again 1, 1, 1, and 1, and you get negative 0.4. Okay, so once we have determined all the parameter, the next step is we have to substitute all the parameter into the main equations. So if you still remember here, okay, our equations. So we have V dash, we already calculate, and CFIC, okay, we have done already. So we have now find this parameter, we have find this parameter, we have find this, and C dynamic, because of our have been stated here, okay, have been stated. So for C dynamic, which is 4 Hertz, where we have 4 Hertz, which is more than 1 Hertz, so therefore our C dynamic is equals to 1. So we have done C dynamic as well. So because of that, then we need to substitute all the equations into the design pressure, wind pressure. So now first calculate the design windward pressure. So the design of the windward pressure is equivalent to 0.5 of the density of air, okay, and then times with the V design speed, okay, V dash, and then the coefficient factors for aerodynamic shape, which is CFIC, we have calculated just now, and then you need to calculate for the dynamic, where we already know it. So in this particular case, so the design wind pressure, okay, at this particular point, if you still remember, we have a variety design speed, okay, whereby we have 10, 20 until 40. But for this particular case, I will show only for the 40 designs, windward speed, and the rest you can calculate on your own. This is just for the sake of these examples. So here you can have 0.613 times width. So find your v dash, okay, design wind speed at 40 meter, okay, which is 28.475. okay, you have 28.475 squared time. What is your C fix? C fix, we have calculated it just now. So your C fix is equivalent to, for windward, your C fix is 0.8, okay, 0.8, and C dynamic is equals to 1. So then now you calculate this. So what did you get? So calculate this, 0.613 times 28.475 squared times 0.8 times 1. So you get 397.6 Pascal. Okay, or you can have divided by 1000, you will get 0.397 kilo Pascal. So that is for the windward. Okay, so now let's calculate for design pressure for the leeward pressure P. So this is windward, and here is leeward. Okay, so for this one, okay, for leeward, so again you will have 0.5 air times v dash squared times C fix, okay, and times with C dynamic. Okay, so here again you will have the similar one, 0.613 times, what is your V dash? We still use the same, which is 28.475 squared, and your C fix, okay, so C fix here you have to get the leeward C fix. So here the leeward C fix is negative 0.4. So then include it into the equations, negative 0.4. So make sure it's difference. Here windward and here is leeward. Leeward is negative. So dynamic factor is 1. Finally, when you calculate, okay, if you calculate by calculator, 0.613 times 28.475 squared times 0.4, and then you get negative 198.8 Pascal divided by 1000. So you get, or you have here is negative 0.1199 kilopascal. So this is for the leeward. Okay, so the main objective, if you still remember, we wanted to know what is the wind pressure acting here, and the wind pressure acting here is supposed to be the net wind pressure. Okay, so basically you will have what we call that, this is the windward pressure. Okay, if you have here, this is your buildings. Okay, so this is the windward pressure. So here is the suction side, which is what we call as the leeward pressure. So we need to have the pressure, which is the net. This is the windward and leeward. We need to have the net pressure. So then your net pressure is, okay, so net pressure, which is the one that will acting at your building, okay, is given as 0.397 minus 0.199. Okay, so then you will have 0.397 minus, so you need to plus 0.199, so you get 0.596 kilopascal. pascals, or equivalent to 0.596 Newton per meter squared, kilonewton per meter squared. So now your design pressure is 0.5 96 kilonewton per meter squared, which, if you still recall earlier when I did these examples, I did highlight it to you here, if you still remember, in our notes. Okay, the minimum wind pressure must not be less than 0.65 kilopascal. Okay, so here, if you look, our net pressure is less than 0.65 kilonewton, okay, kilonewton per meter squared. So because it is lesser than 0.65 kilonewton per meter squared, then we have to use, you have to use our net pressure is equivalent to our minimum pressure, which is equivalent to 0.65 kilonewton per meter squared. Okay, so we have 0.65 kilonewton per meter squared. So in other mean, it means that our wind pressure that we wanted to find is 0.65 kilonewton per meter squared. So here, okay, so then finally we can try to get what is our base shears and overturning moment. So we now have our windward pressure and leeward pressure. So calculate the base shear and overturning moment. So how can we calculate our overturning moment? So we now know that the wind pressure that we are trying to find just now, that we have found it just now, is 0.65 kilonewton per meter squared. So we then now to look at the forces acting on the building. Okay, so forces on the buildings, so then we have to have the Z and F. Okay, so Z and F. Okay, so here Z is height in meter and F is kilonewton, which is the kilonewton per meter. Kilonewton is our loading. Okay, and then this is, you can have the F times with Z, which is the kilonewton meter. So create this table. Okay, create this table. So then so Z, our building is 10 meter, 20 meter, 30 meter and 40 meter. Okay, so then you put your results here: 40, 30, 20, 10 and 0. Okay, because this is 0. Okay, so here you can find what is your force. Okay, what is your force? Alright, so for 40 meter, we now know at these times, though earlier our V dash is different. Okay, our V dash, if we calculate earlier, if I show it to you just to recall, though our V dash is different, but when we calculate for the pressure, it is still less than 0.65. Therefore, in our case, the whole floors, okay, the whole levels in the buildings are being applied 0.65 kilonewton per meter squared. Let's say we have a different V dash, so probably at this level is 0.5, here 0.65, and so on. Okay, it depends how we calculate the V dash and so on. But in this case, because of we have a minimum value that need to be applied, so therefore we apply those minimum. So here you can calculate. Okay, So here is 0.65 times with 8 times with 5. Okay, why 8, why 5? Because you have 8 meter at the back, okay, which is this comes facing 8 meter width, and why 5? Because the whole length is 10 meter. Okay, here is 10 meter, this is also 10 meter, 10 meter. So you distribute up at this point. So at that point, okay, you multiply with 5, so then you get 26 kilonewtons. And for 0.65 times 8 times 10, you get 52. Why times 10? Because here they are sharing. Another way you can see that, meaning that 0.65, okay, 0.65 times with the width, which is, this is the width, times with 8 meter, okay, 8 meters, and then you times with 10 meter divided by 2 to get your force. So here if you did that, okay, you will end up with the same 26 kilonewton. 0.65 times 8 times 10, you get 52 kilonewton. So this 52 kilonewton, okay, is, sorry, not divided by 2 yet, divided by 2, you get 26 kilonewton. So 26 kilonewton means 26 kilonewtons up there and 26 kilonewton down there. So the same thing when you apply here for this level. So meaning that here, when you apply for this level, you need to add up another 26 because they are sharing forces here. So that's why in the middle they are doubles. Okay, 26 times 2. Okay, so here is 52, and you can see here 0.65 times 8 times 10, 52, 0.5, sorry, 65, 8 times 10 equals to 52. Here 0.65 times 8 times 5 equivalent to 26. So you calculate this, okay, so F times Z, so 26 times 40, 26 times 40 is 104. 26 times 40, 26 kilonewtons times 40, 1040, and here will be 1560, here will be 1040, 520, and 0. Alright, so by having this is going to be our total shear. So total shear, which is total FV, is equivalent with 208, which means 26 plus 52 plus 52 plus 26, you get 208 kilonewton. While, okay, meanwhile, overturning moment, okay, overturning moment is equivalent to this plus this plus this plus this. Okay, so then you will end up with 4160 kilonewton meter. So for this particular structure, under the design wind pressure, you will end up with overturning moment, which is M equivalent to 4160 kilonewton meter, and V, okay, the shear is equivalent to 208 kilonewton. So this complete the examples for wind loading. So complete the examples for this wind loading. So we now know what is the design wind pressure, and we now know what is the determined base shear, what is the base shear and overturning moment. Okay, so to see your level of understanding, now I give you a simple exercise, okay, which is design signboard. The concept, procedures, and etc. are the same as what we have learned in examples. However, here we have a design signboard instead of enclosed buildings. So you have to look at the clause, whereby when you have a difference, what we call it, when you have a different types of structures, what does it will affect it for in designing the buildings. So you have to check the clauses, okay, and you have to check the clauses. One of the things that will affect it is the aerodynamic shape factors. You have to check whether the enclosed buildings, they have their own own way how to calculate the CFIC. And if you look at the freestanding hoardings or walls or signboards, okay, they have their own way how you can calculate the CFIX. So you have to check other clauses as well. What does other different things that will govern the behavior when you designed the signboard, that will govern the behavior of the design wind pressure. So this is the questions. The signboard is 15 meter with 10 meter, and then you have 30 meter, and the proposed locations is at Pulau Pinang. Frequency is 1.2 Hz. Assume directional effect hill and ridges as well as shielding are negligibles. The questions: assume wind acting normal to signboard, determine the base overturning moment and base shear, neglect wind load on column. So you're supposed to allocate 45 minutes for this example, for this exercise. Good luck.